session. The speaker is Dominik Schneble, and the title of the talk is Probing Disorder in Lattice-Trapped Bosonic Mixtures. Please, Dominik.
Yeah, so first of all, I would like to thank the organizers for inviting me here to this very stimulating workshop. And I want to talk about basically two, or maybe if time allows, three experiments where we looked at effects of order and disorder in mixtures of bosons in optical lattices. And since these are basically, it's a mixed bag of experiments, it's hard to give a common introduction to this. Maybe what I can say is that the techniques that we used are what holds those experiments together. The first experiment is very simple. You take an optical lattice with, which is very deep and has atoms trapped in it, and you make this lattice state dependent such that the second species does not see it and overlaps with it. And what we do then is we impart kicks to this species, the blue one here, and ask what are the effects of the trapped impurities. The second experiment is, as you can see, rather similar, except here we start with a species that is very far away and impinges on a, I would call this now, even though I'm not allowed to do this, crystalline structure of atoms, and we ask what can we learn about the properties of this crystalline structure through the scattering properties. Okay, so by way of an introduction, let me maybe quickly say something and repeat what Alain Aspect showed yesterday on one of his slides, the different regimes that one can have if there's no interactions at all, and one has this order, then one gets these very beautiful results of Anderson localization. On the other hand, we all know that in 1D, one gets the Tonks gas if the interactions are strong and if there is no disorder present. Now, if both disorder and interactions are present, one can get new phases, the so-called Bose glass, and I'm happy that this Maciej-Levenstein, we have an absolute expert for this here. So maybe let me just give you a qualitative kind of introduction to this Bose glass phase. So if you think about a crystal with a unit filling, and you are hopping and interactions, then of course what you get is the well-known phase diagram with the mod lobes here and the superfluid around it. Now if you introduce this order, in this case it's this order in the lattice depths, then you get another energy scale in here, which is basically the amplitude of the disorder. And what that does to your phase diagram is that it changes it such that the mod lobes are now surrounded by a new phase, which is called the Bose glass, which separates the mod regime from the superfluid regime. It's a gapless phase, it's insulating, and it's compressible. So far the expectation. Yeah, and then if the disorder gets stronger than the gap, then those mod lobes appear completely, and one ends up here basically with a more or less homogeneous phase of the Bose glass, which is separated from the superfluid. There have been some experiments on this. An early experiment by Impugio's group, then experiments by the Marcus group, and also I should say that as far as the compressibility is concerned, there are now indications from Tilman Esslinger's group that this has also been seen. Just to make one point, which I think is pretty important for the Bose glass, is that this is the transition from superfluid to the Bose glass is driven by interactions. So if you increase the interactions, you basically go from here to here. So you go from the superfluid into the Bose glass. So you have this order of interactions, they both sort of act together. And that is different from the so-called Anderson glass, which we heard about yesterday, where interactions basically destroy the localization. So if you have energies which are below a certain mobility edge, you are localized. If you are above it, you are not. Here for the Bose glass, they both act together. Okay, so in our experiment, as I mentioned, we have two species in an optical lattice, which is state dependent, and we implement this order in the following way. We start out basically with a gas here, and we add an incommensurate lattice. So this is just repeating basically what Ingushio's book did. This incommensurate lattice adds sort of pseudo-random energy offsets on sides, and if you look at the kind of disorder you get here, then you see it's still fairly deterministic and regular. For example, if you look at the distribution of side offsets and the autocorrelation, you see that this is still very, very regular. It oscillates. So it's not really an ideal kind of random realization of this order. And so we just use this as some kind of background measurement. The other method that we use is that we use the state-dependent lattice as before, but now it is state-dependent. Here it wasn't, here it is. And on the lattice, with randomly localized impurities. And then if you look at this kind of disorder, you see that, I mean, there's residual oscillations here in the correlation function, but it's a much better implementation of this order. And then, of course, a third method would be to use laser speckle, but we didn't have the technology for that, so we just didn't look at this. And there are groups who can do this much better, of course. Now, how can we make lattices that are state-dependent? Well, we use rubidium and alkali, and you can simply imagine when you look at the fine structure here that if you use circularly polarized light, which is tuned between two transitions, here are the D1 and D2 line, then you get optical potentials. One is attractive, one is repulsive. They both add up, and you can make it such that there's no potential left. So you shine in light, and there is no optical potential. But that, of course, now depends where you are. If I take this state here, there is no state down there to which I can couple, so now I get the full effect. Actually, this one, yeah, I'm already tuned with respect to this transition, and so I now have two potentials, one for the blue state, let me call it like this, and one for the red state. One is 0, the other one is not. Okay, and yeah, we use the standard alkali here, rubidium, two hyperfine states, either 1 minus 1 and 2 minus 2, and we use microwave radiation to sort of prepare mixtures, and then that's how we enter our optical lattice. These experiments were all done in 1D. So we have a two-dimensional lattice that we start out with, which creates tubes. Those tubes are relatively narrow and deep, so we have a 40 recoil deep transverse confinement. And for the sake of the argument, I can just concentrate on one of the tubes now, and we get the results for our entire system just by averaging. So in the tube, we are still relatively superfluid, so the living parameter is 0.6. So yes, it's not perfect superfluid anymore, but it's still coherent enough. And we typically have 100 atoms per tube. Okay, so how do we implement this order? We start with this tube, and we ramp up a primary lattice along the tube direction. Then we apply microwave pulse, which creates a superposition of states in this lattice. And then we add the state-dependent potential, and magic happens. We confine the atoms in there. Of course, you say this is not possible. Why should this realize one realization only, not all others? That's completely true. What we really should deal with here, at least conceptually, is a superposition of many different realizations of this order, which all act at the same time. And there have been a few papers which looked at this, and they predicted or concluded that even though the system isn't fully comparable to a, let's say, speckled disordered system, because we deal with all those different realizations at once, it still should show Bose-Glass behavior. Okay, and then the alternative here is the weak incommensurate lattice, which creates those offsets. And we characterize this by primary lattice steps and then the secondary lattice steps, as prime here for the incommensurate lattice. Okay, so we characterize our system. Yes?
Isn't it so that the superposition really in each run is somehow reduced to one of complete periodization?
It shouldn't actually, well, I mean,
on the size.
It depends on the size and the time. I mean, we have residual magnetic fields which lead to dephasing, and so also in our experiment we have many tubes, and so it's not really experimentally accessible to ask this question, because we are also averaging over many tubes at once. But it's definitely an interesting kind of consideration. Okay, so we modulate the lattice to probe the excitation spectrum, and what we also do is we run the lattice down to some finite value of this primary lattice, do some kind of phase shifting, and then measure the width and the visibility of the superfluid. Okay, so here's just a tube with the primary lattice on. You see that as you go into the mod regime, you see those resonances, which are telling you that you have a strongly correlated system. And when you add the impurities, you see that this structure goes away. Basically, you get a flat excitation spectrum. And by the way, you see the same thing when you use the two-color lattice with comparable kind of amplitude modulation of the disorder. So there's nothing sort of different that one can see here between the two realizations. In both cases, the distribution of side offsets is rather broad. Yeah. So we are larger than U, and so we don't expect any kind of modness there anymore. Now a second measurement that we did is a simple phase imprinting technique. So we give the system a short kick that imprints a phase, and if the system is superfluid, it will then move afterwards, and if not, if it's in mod state, it will not react. So yeah, so we kick and then we see what's the velocity afterwards, and do some sort of repeated measurements of this to get better data. And what you see now is the following. This is just here a tube with a primary lattice. Yeah? So as you grow the lattice, the system goes from superfluid to mod insulating, and for our parameters, the calculated transition is actually around 6. So that kind of makes sense. And also, when we look at the peak width, which tells us how superfluid we are, you see that the peak width is pretty low here, and then at this value where sort of we have this peak, the peak width starts to increase. So that's just as a kind of reference measurement. Now we add the impurities, and what you see is the following. First of all, your phase is less well defined, but what's more important here is that the point at which you reach the insulating regime is shifted downwards to smaller values. You see the same thing here for the peak width, that it starts to increase before, earlier than before, and this value at which it starts to increase is the same as we have at this point over here. Okay, now the surprising thing, at least for us when we did this, and it's still kind of surprising, is that if you repeat this experiment with the bichromatic lattice, so basically in Gouchot's experiment with this sort of additional technique, you see again that the system is less superfluid, and the peak width is a bit worse, but this point is not shifted. So there's no shift of the critical point to smaller values, and that's pretty robust finding. We can vary here the height of the disordering lattice, and this point where we sort of hit 0 is fairly constant. So it's not really obvious why this is so. We are happy at least that what we see with impurities is roughly what one expects. Yeah, so if you think about the not disordered case, and say you have to transition from superfluid to mod somewhere around here, then clearly this is shifted to higher values here in this diagram, which means that this occurs at smaller values of u. This thing is bigger, so smaller values of u, meaning we have this earlier in our diagram. So that seems to make sense. With incommensurate lattice, well, there isn't really a good treatment of that. We found one statement in the paper here by the Geneva group, where they say that correlations are important. Yeah, in order to have an effective action of this order, it has to be uncorrelated. And this is definitely more the case here for the atomic disorder than for the incommensurate lattice. Okay, so the second experiment is here, the experiment where we move the matter wave into this region with localized atoms. And yeah, so I mean, I won't tell you how we do this. Basically, we can apply a field gradient, or we can move the crystal into the matter wave using the tuned laser beams. What we see is always the following. So let's say the crystal, colors here are interchanged, I apologize for this. The crystal is in the mode regime, so in time of flight you don't see anything. But what you see here for the matter wave is basically an unperturbed part, always, yeah, zero momentum, and then something which is coupled out. Now, why is this so broad here? It's simply because we have a one-dimensional system, and when we let things go, it basically explodes. So this is an uninteresting direction, and so what we do is we just sum up over this direction, and then get sort of one line on here. And what we do here is we vary the speed of the relative speed. And what you see is always that there is some part of the matter wave which is not affected, and then another part which is coupled out, sort of at the momentum that one expects, simply from specular reflection. However, when you sort of go along this line and you sum up, you see that there now are peaks. Yeah? And so those peaks, they appear at 1 recoil, at 2 recoil, at 3 recoil. That's exactly Bragg peaks for the matter wave. And so what one learns here is that, yeah, you can use the matter wave to sort of learn about the periodicity of the crystal. That's one thing. The other thing that you can learn about is when you look at the structure factor here, which decomposes into periodic part, and the form factor, so you can learn something about the on-site distribution of the atoms on sites. And so what we can do is we can just melt this crystal, melt in quotation marks, by ramping down the depths of the state-dependent lattice, and so it becomes basically featureless. And what you see is that this Bragg peak, this second-order Bragg peak here, just vanishes here. And the way it vanishes is simply, you can calculate the structure factor of the target, and what you find is that this is exactly like a de Beauvoir factor for thermal motion, except that the amplitude of the thermal motion isn't really due to thermal motion here, but this is just the harmonic oscillator width of the atoms in the lattice wells. And so you could say, in some kind of stilted way, that we are measuring 0-point fluctuations here, and that this is a 0-point de Beauvoir factor that we're looking at. Okay, now when we are at this point, without any Bragg peaks, we see something else. We see that the matter wave, which is, so what we did here is what the matter wave came in at 2 recoils and then flew on. So these are atoms to which nothing happened, but you can see that some of the atoms actually get stuck at 0 velocity. And what happens, of course, is momentum has to be conserved. We see that some atoms are kicked out from the target. And so what's happening is either we pass through, or we are exchanging momentum. And so this is a nice example of a one-dimensional collision, where Maxime has also done some sort of fundamental derivations. And it's a little bit like the experiments of Dave Weiss. They took a gas, split it in one, and then in 1D let it recombine. And what he saw was that the atoms magically pass through each other without colliding. Of course, for indistinguishable particles, you cannot distinguish reflection from transmission. And so we can do this here, of course. And the nice thing about sort of doing it this way is that you can directly read off the reflection probability from just comparing this number with that number. And we didn't do this very carefully, but yeah, we have one value here, I think it's 14%, and that seems to fit pretty well with what one calculates based on that paper. Now, these peaks here, or these atoms which get stuck, they are not there when you have Bragg reflection. Yeah? You have a peak then here. There's nothing here. So why does this go away? This is a simple energy argument. When one of the species is free, coming in, and the other one sits in the lattice, for the same momentum, they have different energy. One sits in the band structure of the lattice, the other one doesn't. And so this momentum exchange becomes off resonant. And so the deeper the lattice is, the more energy one violates, and so the less probable this process is. And for us, I mean, we have a certain energy uncertainty simply because the pulse is short of the matter wave, it's on the order of a millisecond or less. And so we can nicely model sort of the vanishing of this Newton's cradle with lattice steps, like just applying Heisenberg's uncertainty principle. Now, what's that good for? Well, it's definitely sort of nice from a standpoint of fundamental physics and seeing nice things, being able to play around with things, but it could also be very useful for the characterization of systems, simply because unless using light to do things, it is very easy to tune the Broglie wavelength of a wave, and so we are not limited by any kind of structure size, but we just come in with a higher speed. Okay, so so far so good. Now let me tell you about one other experiment, which is a little bit related to what we did here in the first part, in terms of we're dealing with disorder, but it's a different kind of disorder. What we do here is that we take a Bose-Einstein condensate and our incommensurate lattice, and what we do is we flash the lattice on periodically. Yeah? And so every time you flash on the lattice, you diffract. Yeah? So you produce Kapitza-Dirac diffraction pattern. And so as long as you have a single frequency only, this maps perfectly to the kicked rotor model. Yeah? So you have here a series of kicks. Every time you impart momentum, and in between you evolve freely. Yeah? And so there's a series of kicks. And by simply going to a momentum or plane wave basis, you can map this Hamiltonian to, or you can write it in this form, that you have this kinetic part here, with some kind of quasi-energies which are given by the corresponding kinetic energies that the particles have when they fly out here, corresponding to 1 h bar k, 2 h bar k, and so on. And you have a term which gives you transitions between the momentum states. Yeah? So every kick basically brings you, let's say, from here to here, and then from here to here, and so on. So this is a little bit like hopping around in a potential landscape. And it depends now what the period is of those kicks. So if we do this resonantly, I mean, okay, so the first kick produces some atoms which fly out. Each atom evolves with a phase corresponding to its kinetic energy. And so at some point they will rephase. If then the next pulse comes, it will sort of lead to constructive interference. And so modulo 2 pi, one can basically say the phase is then flat, yeah, for the next pulse. And what this means is that if you start with a state which is localized here, let's say the BEC, in momentum space, the first kick brings it there, the second kick brings it there, and so on and so on. And so you get a ballistic spreading in momentum space. So this is for the case that you are resonant. This is sort of a Talbot resonance condition. Now, if you are not resonant, what happens then is that after many kicks, your potential landscape or pseudo-potential landscape modulo 2 pi looks rather scrambled up. Yeah? And so it becomes a randomized kind of potential landscape. And now your kicks, they will lead you out here, and then the next one will lead you back, and so on. And so you're not going anywhere, you're getting stuck. And this is known as a dynamical localization. It's a direct analog to Anderson localization. Okay, so that's nice. But what did we do now? We used two lattices. Yeah? So we get actually a much more complicated pattern of modes, which are now characterized not only by how many quanta of the sort of blue photons do we have, but how many of the red ones. And so it's essentially a two-dimensional system, a two-dimensional problem. However, when you, I will get to this in a second, so your momentum is so and so many quanta of the one lattice and so and so many quanta of the other. Now if you calculate the Hamiltonian, you find again that you get these sort of transitions between the momentum orders. So you tunnel either between all the blue ones or all the red ones. But the kinetic part, you have to square the momentum, And what you see is that, yes, you get the kinetic energy from the first lattice, corresponding to the first lattice kicks, and to the second one, but there's also this mixed term. So this is no longer independent. So it's a two-dimensional problem. One could say it's a two-dimensional disordered potential landscape, and you are sort of localized within that if you try to move. But there's this additional coupling, and what we see is actually the following. So for a single lattice only, could be one or could be the other, both driven off resonantly, we see that the first kick does something, so it diffracts, produces an initial pattern, but then if you repeat, and there is more and more, you don't go anywhere. So after 40 kicks, it still looks the same. So that's dynamical localization. Now, if we add the second lattice, however, what we see is this. So the first kick gives you a more complicated Kapitz-Dirac pattern, and then after many kicks, you see that you get a very broad distribution over this momentum basis, and this distribution is actually Gaussian, and so it looks like classical diffusion. Now, one can study the dependence on the kicking strengths, and so you see that there's a large region here where you sort of localize, and then a region where you start to delocalize and sort of start to diffuse out. And if you go along this line here, chosen for convenience, equal kicking strengths, you see that around 2, in this units of kicking strength, you start going from being localized to delocalized. We did some analysis, a Fluke-based analysis, and that shows also transition on. So the interpretation of what's going on is quite non-trivial, and I don't claim that we really understand it. So basically we know that in two-dimensional disordered system we should be localized, and here we are then not localized anymore. Some classical behavior pops up, and that's obviously due to some kind of symmetry breaking here, because we are coupling the two directions together.
This is predicted by that model you wrote down, right?
Excuse me?
This is predicted by the two-dimensional model that you wrote down.
It is predicted. I mean, it comes out in the simulations, but it doesn't really lead to understanding yet. We found, however, one paper. Hold on, this is here. We found one paper from the late 80s, which was half computational, half not, where they they asked basically, okay, in terms of classical chaos, how can this arise in a quantum sort of system, and what's the simplest possible quantum system in which this can arise? And they came up with this example of two coupled kicked rotors. And so we are at least consistent with these predictions. However, a real intuitive image of why this behaves like that is also not there. So it's certainly interesting here. We see some transitions, but I would like to understand it better. Okay, so I'm probably a bit ahead of time simply because I started earlier. So let me come to the conclusions. So first, I hope I was able to show you that state-dependent lattices offer some kind of new possibilities to study novel effects in optical lattice systems. Yes, one can use localized impurities to implement disorder. do some kind of studies of behavior, of insulating behavior and localization. Then the second part, use matter waves as a probe for spatial order and also band structure excitations in a ultra-cold atom system. And finally, that was the motivation why we did this pulse experiment. We wanted to see, does this order always lead to localization? Yeah. And we said, okay, let's try pulse disorder. And so, in that sense, the incommensurate lattice could be viewed as some kind of disordered construct. And if you pulse this, we see that no, it can actually induce transport rather than inhibit. So this I would like to conclude and also acknowledge my group. So this work was done in large parts by Bryce Gadway, who is now at Chile in Chunier's group. Also Daniel Plateau collaborated on the matter wave diffraction experiment. He's now in Michael Köhl's group at Cambridge, and another PhD student got on that was Jeremy Reeves, and we have a new addition, Ludwig